Hi, I'm Oliver Gao. I'm the director of Cornell Systems Engineering Program, and I have been conducting these systems conversations with our prestigious speakers that we brought to Cornell to talk about the system-related challenges, solutions, as well as opportunities. So today, I'm very delighted and honored to have Dr. Rafiqul Gani with me today. And Dr. Gani, actually, he retired at the end of 2017 as a professor of system design at the Department of Chemical and Biochemical Engineering at the Technical University of Denmark. And he was a former head and a co-founder of the Computer-Aided Process Engineering Center, which is, I would say, kind of CAPEC. Yes. So Professor Gani, he is also the former editor-in-chief of Computers and Chemical Engineering Journal. So he is the ex-president of EFCE, which is European Federation of Chemical Engineering, and finishing his second term at the end of 2017. And he is a member of the Danish Academy of Science, a fellow of the ECE, and also a fellow of IChemE. So I do want to mention that Dr. Gani, not only a great educator and researcher, he is also, I believe, an entrepreneur. He is actually the co-founder and the CEO of the company, which is PSE for Speed, providing innovative, accurate, and consistent engineering solutions very fast to industry clients. So of course you can see I have a long list that I can go on, but I think now I would like to turn to Dr. Gani. And, look at your career, look at all the wonderful work you have done. I think one thing, including myself and the audience, we are very curious about you yourself as a person and your career. So whatever you would like to tell us about yourself.
Well, let's say I was always very interested in developing model-based systems. So understanding the system and then developing the model for that system and then using the model to develop different kind of computer-aided tools to solve problems. This was always my interest. My PhD was on that. After that, I was lucky to be able to work in an area in the department where I could develop these. And I would say that I was lucky to get very good students who were interested in this. And so we were able to develop. But my always interest has been that I would like to understand the system where modeling is very important, and then using the model to develop solutions that can be innovative, can be new, can be challenging.
How did you see your career evolved across different stages, and how, of course, I know like when we were trained as a PhD student, I believe most of the time our advisors would tell us for the PhD research, focus on one specific thing and dig deeper into that thing. And even after we started our tenure track of faculty, before we get the tenure, I think the senior member will always tell us, focus on the thing that you are doing the best and dig deeper into that. So, but now like of course you're way across, you're way past that state. However, how did you see, your research evolve and your view change?
I would say that I was again very fortunate to have as my PhD supervisor, Professor Sargent, who is regarded, at least in the chemical engineering area, as the founder of process systems engineering, as we know. And at the time when I was doing my PhD and the other people who were doing their PhD projects under Professor Sargent, we could see that it was a wide spectrum of topics, all of them with a systems approach, finding clever numerical mechanisms to solve problems, get intuition. That stuck with me always. And then when I had the opportunity to develop my group, this was always the focus. And what I was able to do in Denmark was that I was able to set up something like we call an industrial consortium of member companies. And I would tell my PhD students, look, you're not only developing something theoretical and something clever, but you have 3 years. The PhD in Denmark is 3 years.
Mm-hmm.
You have 3 years to convince at least one company to use your tool. And
Wow.
if you can do that, then you will feel it is worth doing your PhD. And I think they all managed to, within those 3 years, get at least one company to use what they were doing. And that was the motivation and challenge for us, that we would find ways to solve problems that were of industrial importance as well.
That was a wonderful point. I think really, a lot of times for PhD education, like of course, a lot of advisors guide the student to publish papers, but without telling the student why do they need to publish.
Yeah, exactly.
So I think you made a very good point. And also of course for a lot of academics and even for entrepreneurships, we know that very well known kind of Death Valley. A lot of research get to a certain point,
Yes.
it's dead. But I think like your mechanism, the way you just talk about, it's really, I think, really bring the research down to its ultimate goal.
Yes. And so we had always this approach that we are going to develop these things. And yes, we can think of a topic that at this moment industry is not interested. But we will find a way to get them interested in it.
Mm-hmm.
So sometimes we started the project without any funding from industry, but by the end we gradually got the industry to be interested in it and then use more and more things with us.
That's wonderful. So I'm just curious, how did you come up with that idea? Even to you, it seemed like very simple. However, to me, I think it's really innovative.
Well, I can say that both my students were good students, and if we thought something that was interesting and we believed in it, we just pursued it. I can tell you that once I approached a very well-known big company that we are trying to do this. Would you give us a case study? They said, no, we have all the tools. We solve this regularly.
Mm-hmm.
So we said, okay, we will tell you next time you come what we have developed, and then you can see. And then after 6 months, they came to our meeting and they saw, and then they said, by the way, can you send your student to visit us for 3 months? And then we developed a very good collaboration.
That's great. So I think, this is really important. Maybe we can spend more time to kind of, I can.
So here I can just add one thing is
Yes,
that it's not only enough to tell that we can do something, but we have to deliver to the companies.
Mm-hmm.
And that delivery of what we claim is very, very important. Otherwise, they will lose confidence in us.
That credibility will be hurt.
Credibility is very important.
So you mentioned the students have roughly 3 years
Yes.
to build the idea, build the tool, and also find a place
Yes.
to apply that. So among all the students that you have advised, how many of them, what proportion was able to meet this standard?
I would say maybe the ones that I would be really satisfied with would be between 60 to 70%.
So what are your tips to at least so far, even though we've been talking for about probably 5 minutes, but I feel you are really a very inspiring, I think, educators. How did you get these students?
I would say the ones that was really good, I was teaching also courses at the master's level. And in Denmark, the system is that the first degree at that time was a master's degree.
Mm-hmm.
Now it's a bachelor plus master.
Mm-hmm.
And before they start PhD, they need to have the master's degree. So I was teaching a process design course.
Mm-hmm.
I was teaching separation course. I was teaching some product design course. And I could see from the teaching who were likely good candidates. And I would propose to them that they do a master's project with me, because that they have to do for their masters. And if everything works out, they can just continue with the PhD.
You have a very good pipeline.
Yes, I had a very good pipeline.
Yes.
And I would also say I was lucky with some of the foreign students, that they were interested, because within chemical engineering sometimes it's difficult to get students who would have a good understanding of the systems approach, can develop software or computer-aided tools. And I had a good collection of students like that they were good in chemical engineering, but they also understood the software architecture and the importance of that.
And then, say you have this pipeline, or of course people from international background, they came to you. The reason I'm asking this because we're also advising, especially PhD student coming to this system program. They have all these different background. Not all of them are very well prepared for example, the quantitative analytic skills that you would expect. But what are kind of a little bit more into specific? How did you work with your student to get them on track? And what are the tips or the life lessons?
Well, there are some extra things that come with the PhD study, at least in Denmark, is that even though the time period is short, 3 years, they do have to take 4 courses, equivalent to something like 30 ECTS points. And I would make sure that all these 4 courses are kind of intensive, short 1 week or 2 week courses, basically given by me and my friends all over the world. I would invite them and teach them about, let's say, modeling, teach them about numerical optimization, teach them about integration. So if they took those courses, they at least had the background.
That's nice. So it's kind of like intensive, like a workshop type.
Yes. So 9 to 5 every day, plus some exercises, and at the end of 1 week or 2 weeks, they should be experts in that area.
Wow. That seemed like an expedited.
If they lack the background.
Yeah, that's right. I think it's really good, especially at the beginning when the student came to this program. If they can go through this, if they like it,
Yes.
then they are the right material. Yeah.
The other thing that I was able to kind of decide early on with those PhD students is that who would be good to understand the system and develop the corresponding tool, and who would be good in understanding the system and applying the tool to solve problems. So I made a distinction right away, within 3 months. So those who could develop the software at the same time, they went in one direction. Those who were not good in the software but were good in developing the algorithm, the method, applying the tools, they went in another direction.
I see.
And they worked as a team.
And I think that experience is also very beneficial to people with different strengths and weakness. Yes.
So I basically told them that we were developing what we called an integrated computer-aided system. And I said, look, you all are part of this. And now if you cannot talk with each other, you cannot develop an integrated system. So you have to work out whatever differences you have and develop truly integrated systems. So each of them had responsibility for different modules, and we had to work out the interfaces between them as well as the tools.
I think that's beautiful. So essentially, the students, they are not only working on systems problems. Your group itself,
Yes.
it's a system,
Yes.
right? Yeah.
And whatever we developed, and that's also the good thing with the industry, is that we own these tools 100%. We have not used any external means, even programmers. It's all done by the PhD students.
You had your own startup company. How did it happen? Because I think these things. Yeah.
This is only after I retired, actually.
Oh.
Yes.
Uh-huh. So it's that, I actually here at Cornell, we at least I know that faculties there, they can start their own companies. Yes. So they have.
Personally, myself, like my industrial consortium, was working from the time I set up the center. Mm-hmm. So for 17 years, I ran the center, and the industrial consortium grew from 6 members when I started it to 31 companies.
From 6 to 31?
Yes.
In 17 years?
In 17 years.
Wow.
And almost nobody left because they were not satisfied. They left because the company was bought up, or they had internal changes in the company, and this person, who was our contact person, was no longer involved. Now, the reason I did not form a startup company or things was I thought that I would like to spend my time developing these tools and also making sure that for educational purposes it can be used, as well as for industrial we can solve the industrial problems through the consortium. And I felt that it was not possible for me to put on 2 hats. And if I was putting the hat of a businessman, then I would be thinking, oh, that feature would be good for business, but maybe not necessarily for research. And so I concentrated on developing things that had research value, but also had industrial value. And so because the students developing it, they had to get their PhD.
Yes.
And they cannot get their PhD by solving a business problem.
No.
So that's why I never wanted to. I mean, there were people who even asked to buy our software, but I said no. Until I finish, I'm not going to do anything like that.
That's very wise. After you retired, and then, so you are saying like kind of there is one regime, consortium regime, where you don't see, you potentially see some kind of, something that you wouldn't want to start. But then after you retire, you say that. So how is it going, and what motivated you?
So also while I was, let's say, the consortium, the objective there was that they would use our systems ideas, systems approach. And this is what I was trying to get them. And now that I've retired, I call myself a freelance professor. I go around different universities, give courses, short courses, which I like very much, from 2 days to 1 week, maximum 2 weeks.
By the way, we'd love you to be here more often.
Sure, if we can find a way to give a course that could be of importance to you, I would be happy to.
I'll keep that in
mind. So that is one thing, is that helps me to convince, if I'm able to, that this system's approach of formulating the problem, solving the problem, can help them from an education point of view. And then from the industry point of view, what I can see is that I'm trying to show to them that we can solve these problems like speed very fast. Yeah. If we know, or those who want to solve them know which tool to use, what is the best way to solve the problem, understand the problem, formulate the problem, find some clever way to solve it. And we just started officially the company working at the start of this year. We have already finished 3 projects with companies, 2 actually from China. And we could show them that using our tools, we could reliably solve the problem much faster than they expected, and very reliable solution. And during this trip now, I'm going to talk with 2 other US companies. to see if we can convince them that these tools are there. And what it can do is, it's not competing with other tools that are there, but what it can do is increase the efficiency of people using these tools. And just as an example, a chemical process simulator that you may well know.
Yes.
How much time does one use trying to set up the problem for this? Sometimes quite a lot. Now, if we can provide them a tool that will automatically do that, intuitively, not totally automatically, interactively, they can save order of magnitude of time. So instead of 1 week, they can solve it in 1 hour. And this is the time scale I'm talking about. And I'm worried that what I'm thinking of now, and I've not found a way, is that how to use it for teaching also, because if the students get it, they will not learn anything. They will solve the problem, a design course, in 1 week. So how to introduce these things and the systems approach and the tools in a way that they will learn also at the same time. Otherwise, they will take the tool and solve the problem without learning.
That's a very fundamentally critical problem that you raised. Yeah.
So we develop software tools, but at the same time, we have to think of that should the students just use it as a black box, or should they learn something from it?
So far, I think in all the things, your own career, your own research, and in your startup experience, it's really, I think, kind of give people a sense about who you are, what you have done, and of course, with such a diversified experience and a successful career, and at this stage, I was reading like the abstract you have. So of course, I believe you have already helped companies. Of course, companies serve the society. You have already helped the society to address a lot of big problems, but still, there are challenges and a problem for this society. So now, if we kind of, coming back to kind of, your own area, like from as a researcher, what do you see as a key systems challenges and opportunity for our society nowadays?
I would say that the good thing is that currently, I would say, systems area, whether you call it systems engineering or process systems engineering or systems approach, we have a very good time at this moment, because there are so many multiple challenges we have. The challenge of energy, water, food, environment. How to tackle that? This is a multidisciplinary, multi-scale, whatever multi you can think of.
That's right.
Complex problem. And I think that the systems group are very much qualified to understand this problem, maybe breaking down it into what I call solvable sub-problems, or in another way is tackle the complexity so that these things can be solved. And I would say that if we can contribute to that, this is the opportunity for us as well as the challenge.
And you're right, the challenge is tough, but I think opportunity sounds also very exciting.
Very exciting.
Yeah.
Because there are so many problems there. And I would say managing the complexity is one way, and this is my way, I would say, of trying to see if we can tackle these problems, even some minor problems, and show the world that, look, if you want to take care of the CO2 emission, whether from car, whether from plane, whether from chemical process, together with how the energy comes and what is the source of the energy, and then capture the CO2 and convert it into something useful. If all of these things could be combined together and one could provide a solution that is not a solution for the whole world, but is location dependent, because the problem I will solve here is not the same as in China or as in India or as in Denmark. So it should also take into account data of different places and find out understanding of where is the real problem in each area and how to integrate this and find the solution. Because if we can mathematically represent it, I think we can find a solution for it. Because the numerics is there. But we have to be able to understand the problem and represent it mathematically, which is, I think, lacking at this moment.
So in our community, like research community or higher education community, do you have a rough estimate how many people are thinking in a way like you are thinking?
That would be very difficult to give, but I would say that I know better, let's say, the process systems engineering community within, let's say, chemical and related industries. There, I would say that the PSE area was going down some years ago. In maybe was not that popular some years ago, but in Europe it was always very strong. And now, because people can see that the systems approach actually can contribute, and so it's going up.
What is behind it?
I would say that the problems that people are solving are more related to the challenges we are facing. I would have liked to see more, but I would say that some years ago it was more bio, more nano, but now it's more the popular energy food nexus. Together with that, there is a lot of data, there is a lot of lack of understanding where machine learning and AI, I mean, I was actually surprised that AI all of a sudden has become very important.
Hot.
And hot. And this is good because we don't have the knowledge to, I like to develop mechanistic models. I like to understand and develop from the theory. But the theory is not enough. We don't have the understanding of many things. So there, a combination of mechanistic and database model is the way to go forward. And I think those needs are becoming more and more, people are getting more and more aware of that, even in the social and economic and other areas. And that's why there is much more interest now in the systems approach.
So I think that's great, kind of that probably, and I think naturally leads us to further depths of this discussion. I think closer to like the core area of your research. I think in the conversation you have mentioned, I think early on you said that in your PhD study, you studied this kind of model-based.
Yes.
Development tools, basically probably model-based, in the end it will end up either as a software or as a simulator, right? You do that. And also I think I believe, you mentioned that, so now due to all these key challenges in our society, we need what we call innovative and significantly better solutions, which do not exist today, and which you are aiming to contribute to. So especially there is model-based traditional approach. There is a data-driven. Of course, this data-driven data comes from experiment.
Yes.
Or probably nowadays probably less cost-effective experiment or monitor or sensoring. Yes. So where do you see these two branches of our approach toward scientific discovery converge?
And here I would say, yes, I agree 100% with you, but the thing is that modeling should be an enabling technology or whatever you would like to say, is because we have to think of model also as not just representing the system, but extrapolating from the system. That means a predictive model. can we make a predictive model? And if we can make a predictive model, then we are not bound by the simulator with its fixed model. We can go beyond the simulator. And I will actually show some examples in my presentation today how we can do that. And I think it's simple in terms of concept, that if we take a chemical molecule and then we can say that how many molecules can we make from some combinations of carbon, hydrogen, oxygen. But if we already have some combinations, then the molecules we can make is not that many. But if we say that let's consider only carbon, hydrogen, oxygen atoms, and how many molecules can we make by joining them together? We can make millions. And a computer can help us to connect the atoms together to make the molecules. Now, can we develop those also for chemical processes? If we can break down the chemical processes into the smallest scale and then recombine them, just like the atoms to make molecules, we will find, I think, new operations, new equipment that we did not think of before. It's because we are breaking down the problem into smallest scale and then we are recombining them, just like atoms would recombine to molecules. And this kind of idea can be done for anything. For a car, probably there is already examples that you have different components of a car. Can you combine them together to make a new design of a car?
That's right, yeah.
And maybe the computer can help us to find all the different combinations rather than do the experiments and then find out.
That's true, yeah.
So these are the things that I think, if we can break these things down into smaller scales and recombine them, and the computer can help us to do that, then we would be finding, I think, solutions that we otherwise could not find. So this is one area that interests me very much, and I'm trying to develop even tools that can do this kind of thing. So also modeling, one spends a lot of time in developing the model. Everybody can do modeling, but can they do it very, very fast? And here the computer and systems can help, because the data and the definition of the system has to be given by the model developer. But we can write these days a code that would generate the model code through the computer. And then we would save all the time that somebody is trying to write the equations connected to the solver. All of this, the computer can do it very, very fast.
That's true, yeah.
And I was actually very impressed in China, because we can see this kind of thing, that even in a place where somebody is repairing the shoe, people are actually paying through their iPhone. They just take the barcode and everything is done.
Yeah.
At every level, this is done. This is exactly the same thing. If we can make these automated, a lot of new developments will come in, which will be predictive, not just matching the system.
You know, I really like your approach. I think one key thing that I learned from what you just talked about is, I think, like, innovative ideas do not have to be large scale.
No.
Innovation can happen at an atomic level, and then it can scale up.
Exactly.
Yeah.
And this, I take it from the chemistry, that we know the methods, we know the rules of combining the atoms to form molecules. If we can break down our physical systems into smallest components and combine them together, we could find many different solutions that otherwise we would not consider. And here computing a systems approach that can look at these combinations can help us very much.
So now with this, you say you aspire to make these things happen. I'm curious, what do you see as a major barrier nowadays for you to do what you want to do?
The barrier, I would say, is the application range. That I would say that even with all of these, the promise, in the end, if we cannot deliver to the industry that we can solve some problems that they are facing, then it doesn't go anywhere. So that's one of the biggest challenges, is together with the industry solving some of their problems and showing that it makes a difference. At the same time, the environmental and all these are also challenges that does not require the industry but requires the government, maybe other institutions, to show that there is a way to solve these things.
So you need committed stakeholders.
At least stakeholders that can believe that we can provide the solution.
So now from your point of view, what could be the barrier preventing them from getting this concept?
I would say that that's where we have to be very careful, not to promise too much
And under-deliver.
and under-deliver. So promise little but deliver more.
Yes.
I would say that would be better, that they were not expecting more than this, but we can say, okay, here is a good innovative solution. By the way, we have 5 more that are also very good.
I see. Yeah.
So delivery of the promise is very important. So scope and significance is very, very important to be able to convince the stakeholders or the users that there's a good scope and significance if they believe us, or if they give us the opportunity. So here, what I sometimes used to tell the companies before, and I'm telling them in a different way now, is that, okay, give us a problem. When the student was there, give a problem to the student. The student will use it as a case study for their thesis. You have to allow us to publish that, but we can solve a confidential problem that we will not publish, but you have to give us a problem that we can publish.
Yeah. That's a win-win.
So in that way, we can, with small steps, we can get inside, and then gradually develop the confidence. And now I'm saying to the companies that I'm working with as a business, that okay, give us a problem that you are stuck with, and let us see if we can solve it for you.
I think as a system person, one thing, of course, is actually sustainability of a system.
Yes.
Right? I think you mentioned earlier you built this consortium, this center. During the past, say 17 years, the consortium was very successful. Of course, you build this legacy. Of course, I don't think you would like that legacy to stop with you retiring. So how did you build in the sustainability of that system?
This is both, I would say, while I was still at the university, it was not a problem because the companies knew that as long as I'm there, there would be a continuity of the tools that they were that they were using. So it will not be all of a sudden the tool is not there anymore, and they are stuck with the tool. So we made sure that every year there would be a new update on the tool, and I would distribute the students. We created a kind of a team where one student will be the manager, others will have other duties, and we will continue that. Now, I would say the unsuccessful part of this is that, unfortunately, things did not develop as I wanted after I left with the university. It's not because of the companies or because of the tools. It was just that the university could not think of hiring another person to continue in the steps. I gave them the software free of charge, and they still have the consortium but not the center. But the problem is that if they don't have a faculty and students to develop the things, how long will the companies stay there? Because the companies would expect new developments every year. And so PhD students need to be hired to be able to do those things. And if they don't do that, since they decided to go other directions, so I'm not sure how long that consortium will last.
That's actually why, the reason why I asked that question. It's really, you as a faculty at the university, or you as an asset to the university, it's not only the software you develop. At least from our conversation, what I can see, a bigger asset is actually the way.
Exactly.
Your
I
philosophy,
did,
your
what
wisdom.
I would say is that I did my part, but unfortunately the university did not follow what they promised me, and so I'm not very happy about that. But to compensate for that, I'm offering the same kind of service, not competing with the consortium. I'm saying, okay, if you're not satisfied with it, or if you want other tools, we can do it, as if it was just part of the consortium.
I understand a lot of times there are a lot of institutional problems. However, I think as a scholar, you definitely don't want to have all this contribution to be stopped.
So that's why I'm teaching in many places, and I give the software free to the universities. No problem. You want to use it, I give it free for education purposes. And for companies, if they want to use it as if they're a member of a consortium of a university, we offer those services.
I mentioned our PhD student in system specific. So again, from your perspective, if you reflect on your successful career as a process systems engineer, and then of course even though you retire, I can still see, and I wish, a very broad and kind of very promising kind of rest of the career laying ahead of you. But what would you say to our future systems people, from what you have collected in your career, what insights and advice would you provide to people, not only to system PhD, but also even to people like me? I'm learning a lot from you.
I would say that first of all, believe that the systems approach can actually solve problems. And the way I see the systems approach, or process systems engineering, like I will also show in my presentation, like Professor Sargent said, it's a systematic approach to solve problems with a good understanding of the problem, a mathematical representation of the problem, finding then ways to tackle that mathematics and come up with smart algorithms, or find insights from solution of the problem. And I would say that is so wide in application that it's almost unlimited, the opportunity that is there. And one should find their own areas that they like and develop it without worrying whether they can succeed or not, because if they really believe in it, they will succeed.
Believe means that you have a dream. You plant the seed of a dream in the mind, and then when you have the dream,
yes,
you will be self-motivated.
Exactly.
Yes.
And I think there's no lack of opportunities. The challenge is there, and the means to tackle those challenges one can teach. That, okay, if you have a complex mathematical problem. Here are the tools that can at this moment do these things, but you can develop something more. And one typical example I would say is that once I wanted to develop a very fast and smart way of solving a big mathematical problem. And somebody said, why do we need that? We can just buy a bigger and faster computer. Mm-hmm. And then I thought about it. Well, that's right. I mean, why do we need that? But then I thought, well, if I applied my approach, I would solve a wider range of problems through this bigger and smarter computer. Mm-hmm. So that systems approach is still needed. Doesn't matter whether the computer is faster or not, because it will solve my problem faster, but now I will solve 100 different problems at the same time.
Yeah, I think you hit such a critical point in which a lot of people not often realize it. You can see the value. A lot of people say, "Oh, it seems like Dr. Gani, he made this huge contribution by developing this software." They see this end product as your contribution, but it's really the way, the approach that you produce this product. That's really the real gold behind this.
So that is one, and another I would say that, and this is both good and bad. If we look at the history of, let's say, the development of the chemical process simulators, it actually started from academia. Professors developed them, formed companies, and those companies have become big. And basically, since then, there has not been developments from the academia, and the companies provide all the simulation tools, software tool. Mm-hmm. I think it's about time the academics took over, because how long can you wait for those vendor companies to provide something new that you need?
I think that's again another very good point, which means that these faculties they help this big innovation, and then this marginal value from this big innovation has been exploited by society to a point where we need another fundamental.
So I would say this is a very good time for systems people to come up with, okay, these tools have reached their limit. They can solve these problems very well, but they cannot solve more than that. Mm-hmm. And we need at this moment to solve more than that. Yes. And what could be this? And one in the software engineering, which is also the systems approach, is that can we really have plug and play between not just different software, but we can break it down again into small components like Lego pieces. Mm-hmm. And we develop tools according to the tailor-made tools according to what somebody needs. We don't have to give them all the things that they don't need. We only need to give them the things that they need. Mm-hmm. Can we make it in such a way that we just have to plug and play? Yeah. And this is just data transfer from one end to another end. And if we can work out the interface, this becomes very easy to do.
This kind of, I think it gets back to one point you made earlier. It's really plug and play. It's kind of customized design. Come back to your earlier kind of decompose all these things into modules. And if I have this customer, they want this, and you can assemble it very quickly. Yeah.
So this I would think that this kind of things, again, should come from academia and force and then if they catch up and get the attention they should, then maybe companies can be formed and come up with new set of tools that are not the fixed, inflexible tools that we are using now.
We're getting to the end of the time, but I do want to ask the final question. So far we talk about these tools, this software, and you develop wonderful optimization tools for coming to the use. Especially from a systems engineering point of view, we know that humans play such important role in anything. From the software development to the adoption and application of a tool. So, what are the success tips or failure lessons that you would like to share with our future PhD student in terms of working with people?
So here again, and that's why when I also mentioned that I had students who would develop tools, including the programs, and others who would use. So both with respect to developing a method and then its implementation as a tool, software tool. I was very strict that if we have a method which says do this step by step, then we should be able to solve it by hand first. Take a simple problem, conceptual problem, solve it by hand. Mm-hmm. And follow all the steps. There cannot be any exception. Mm-hmm. And if we cannot solve it by hand, then that method is not complete. If we can solve it by hand, then we already have the architecture for the software. Yeah. And so we ask another student that can understand this, develop the software. So having the architecture and proving it by hand first is very important. And I would not accept anybody's algorithm among my students if I could not see a conceptual example solved every step by hand. Mm-hmm. And so the software also, it should be intuitive, it should be interactive, but it should not be automatic that you just push a button and the result come out. That kind of software is almost impossible to make, I think, at least in the kind of problems we are looking at. So there must be some interactive things, decision-making things, and the way the problem is going and the solution is going, there are lots of solutions possible and lots of paths possible. But the algorithm needs to be able to tackle that. Mm-hmm. And there should be a conceptual example which does not need any software. And so that would be the proof that the method works.
Mm-hmm. Thank you very much, Professor Gani. Very nice talking to you.
Thank you for the interview.